All right, so 10.1.3. I got to be honest, this video took a long time to set up, so I hope I can get through it. I will tell you, I'm going to give you some suggestions for some software, whether it be a actual TI-84 or a simulator like I have. I think you can get an app on your phone, whether it's an Android or a iPhone. I think the Android apps are free. Actually, I could be wrong on that, and I think the Apple apps cost like $5 or something, but still maybe not a bad idea. And I'm going to show you how to do it in Desmos just in case. I think Desmos is getting more popular, and I think it's definitely showing up on stuff like the CASP test and that kind of a thing. So the more familiar you are with it, I definitely think that's good as well. And I don't know, I heard you might be able to use it on the SAT if you can't already. It might be something that comes. So again, it can't hurt to know it. Anyways, comparing data. In the previous lesson, you tried to decide which team was most consistently close to the golf hole. Comparing sets of data is an essential part of the study of statistics. Data is often not meaningful unless it's compared to data. Like, for instance, if I said, I don't know, my fence weighs 900 pounds. That means nothing to anyone unless there's a comparison to say the other fence weighs 9,000 pounds, and you know the other fence is way heavier. So what does your batting average or free throw average mean if you're the only person who has one? Or does your SAT score mean if there's no other scores to which you can compare it? So 1040 says, and I hope you guys are paying attention on this because there's some good stuff coming in this lesson as far as how to analyze the data. Being able to make the data is one thing, but actually understanding what the data is telling you is really where the value is. So as the managing grower of at all organic orchards, you know that the farmer's market will only accept fruit that is above average size for your orchard. However, they do not define how to calculate average with a mean or with a median. Again, mean means you add them all up and divide by however many there are. Median means you count from the outside and work your way in until you get to the middle. So you want to sell as much fruit as possible for premium prices at the farmer's market. So obviously you're going to pick mean or median, whichever one will allow you to bring the most fruit. So your apple crop is represented in the box plot at the right. So this is our apples. To get the maximum amount of fruit to the market, should use the mean or the median or the average for the average. Now, it's not totally obvious to everybody, but if I add all these up and divide, in theory, the average would be brought down by this outlier. So the median is right here. But if I added up all the weights, I would expect the average to be brought down a little bit. And if my average was over here, I would be able to bring all this fruit. If my median is right here, I'm only able to bring this much. But again, if my average was kind of weighted by this outlier and moved back this way, then I could use all this fruit. So I would say that the mean in this example is probably the way to go. I'm going to be able to bring more fruit. So your lemon crop is represented by the histogram at the right. Why do you suppose the right whisker is missing? Well, first of all, I think the right whisker is the same as the quartile. So remember, we have like smallest quartile 1, median, quartile 3, and then the largest should be somewhere over here. But what if we have so many that we have over 25% that are the largest? Then that also becomes quartile 3. So we have a lot of big ones over here. So again, which one should we use, the median or the mean? Well, again, the median's right here, but if half of mine are right here, I think that the average, again, is going to get kicked this way by all these smaller ones, right? So again, the idea, I'm guessing my mean is going to be here, which will allow me to bring more fruit. If my mean is here, I'm going to be able to bring more fruit. So again, I would say the mean. Now, why might the farmers at the other orchards feel like you're being deceptive? Me and the book very much disagree. I don't think I am being deceptive. If you tell me I can bring my average, and I'm going to bring whichever average allows me to have more of. But I guess if these people, for whatever reason, thought the median was the average, then that would have been the way to go. Actually, that's kind of what the book is telling us. The book is essentially saying this, that it's easy to have a little bit of data manipulate the mean. Right? Really, most of the data falls over here, but these over here move the mean in this direction. Really, most of the data is right here, but this over here moves the mean in this data. And I agree with the book on that. It is easy to manipulate data with the mean. So here's the thought exercise. Let's pretend we're in class and everybody in class has like $0 to $20 in their pocket. And then Bill Gates walks in and he has $5 billion for whatever reason. He's carrying around a lot of cash that day. So what would the median amount be? Well, the median amount would be like $18 because Bill Gates would be undone by someone like myself who has no money in his pocket, right? So we'd say like, hey, Oliver has 0. Bill Gates has 5 billion. You guys are all in here somewhere 0 to 20. When I do the median, he immediately gets crossed out and my median ends up here. However, if we do the average, right, my 0 plus all your 15 and 20 plus is 5 billion, it makes, I don't know, maybe the mean at that point ends up being $300 million. Well, that's fine and dandy, and we can all walk around saying, hey, on average, we have $300 million in our pocket. But the reality is that most of us don't. So you can see how easy it is to manipulate the mean and how difficult it is to manipulate the median, because you have to have just as many on the other side to offset the median. So that's what the book's trying to point out here, and I hope I did an okay job of explaining that, why it's easier to manipulate the mean than the median. So really, the book is saying, if we want to use a typical value, the median is probably always going to work, right? We're always going to be able to offset the big with the small until we end up at the middle. Or that's not true for the mean. However, if we get a nice looking bit of data where I have a big one here and a small one here and a big one here and a small one here and a big one here and a small one here and a big one here, then it shouldn't matter if I use the mean or the median, right? But if I get funky data where everything's over here and I just have an outlier or two, I want to use the median. Or if I have, this is known as a tail. If I have a tail, right, or there's a bunch of small data over here, again, I would want to use the median and not the mean. So to sum it up, you can always use the median. You only want to use the mean if the shape is kind of a normal distributed shape. And we'll talk a little bit more about normal distribution at the end of this video. But again, hopefully we're okay with that. Median, always okay. Mean, sometimes okay. It's got to be normally distributed. So we move on here. Home sales in Fancyville and Smallville are shown at the tables below. Calculate the mean and median sales price for each. Compare the Fancyville and Smallville. So first of all, we have the median, and let's calculate the median. It would have been too nice of the book to put these in order from smallest to biggest for us. So here's the biggest. I'm probably going to miss some as I go, but that's okay if I don't go exactly. Here's the smallest. Here's the next. I don't see any more hundreds, so 210 is going to get crossed out by, I guess, this 440. This 230. And this 340 look like they're going to cross out. And again, I'm just crossing out the smallest and the biggest as I go. So that's the smallest and that's the biggest. That's the smallest and that's the biggest. So it looks like I'm coming up with a median of 270. You would have thought, oh shoot, no, that's not true. Let's keep going and try that again. You'd have thought I would have written this down. I can't believe the book didn't put this in order from smallest to biggest. So again, we got a 150 and a 160, so we'll cross out the two big ones. We got how many in the? We got one in the 400s, so we'll cross out a small 200. We have 2, 3 in the 300s, so we'll cross out the 3 smallest 200s. And now I have 2 left. So my median would be the halfway point, so my median is going to be 275. Here, my median, again, I'm going to cross out the smallest. Again, I probably should just break down and write these in order from the smallest to the biggest. There's a big 299 and a small 247, then a 255 and a 289, 272 and a 281. So again, the median is 275. So it looks like they both have a median of 275. But what are the means? Well, I'm going to bring in the big guns. I'm going to bring in a calculator to figure out the mean or the average. So the mean, I'm going to go here. I have Okay, 230 plus 270 plus 150, 305, 240, 280, 1100. By the way, these are all in thousands, right? You're not going to buy a $160 house. but you might buy a $160,000 house. So we're going to divide that by 2, 4, 6, 8, 10, 12, 14 bits of data, and we get a mean of 506,000. If I screwed that up, I apologize. I don't know if I might be off by a little bit, but in theory, if I did, it shouldn't matter as far as proving the point that I'm trying to prove. So here, 255 plus 289 plus 275 plus 247 plus 299 plus 281 plus 281 plus 272, and we're going to divide that by 1, 2, 3, 4, 5, 6, 7 houses, and we get 274. So when we compare this data, which town would we rather live in? Well, unless we end up being one of these people with the super fancy house, right? Our house is going to be potentially terrible compared to Smallville. Smallville, all the houses are sort of in the middle, right? So you got a price like $250 to $300. Smallville, they all fall in that range. Fancyville, they could be as low as 1.5 up to almost $3 million, right? So the question is, which town would you rather live in? Well, you tell me. If I'm normal, it doesn't matter, right? If I'm normal, it doesn't matter. My house is going to be roughly the same. If I'm above average, sure, I'll take Fancyville. I'll live in this mansion here. However, if I'm below average, I would probably rather live in Smallville. So again, you can begin to see what happens when we compare this data to each other. Again, I hope that makes sense, the difference between the median and the mean. Again, it kind of like that example I was talking about with Bill Gates having $5 billion. It doesn't really help us as far as the average go unless we're Bill Gates. Then all of a sudden, having $5 billion is awesome, but otherwise it doesn't matter. So Cyrus has an idea. He wants to compare Fancyville and Smallville's sales like this. And he wants to do what we did in chapter 4, where we kind of come up with this 2 variable data. But the problem with doing that, and I hope this makes sense, is how am I going to compare this house with this house? They don't really go together. It's not like this is one person's height and one person's forearm length. If you'll remember, we did that in chapter 4, right? That makes sense to sort of go one person's height with their forearm and say that, and then the other person's goes like this and the other person goes like this, and then we can draw it. But as far as these houses, like what relationship do they have? They really don't have any. So this is one variable data, and this is meant for 2 variables. So if we don't have 2 variable data, we do not want to do that. And again, it says what would be a better plan? Well, the box and whisker plots that we had used already, where we sort of compare that data, and we're going to do that again today, where we can have dueling box and whisker plots, and that's essentially what we're going to want to do. Alrighty, so at that, we will try and go to the next problems, and we are on 43. Again, a lot going on with this chapter. It's. I hope you guys watch this video or watch other people's videos of this or whatever and have an idea of what all this information is, because there's a lot going on today. So creating histograms and box plots on a calculator. I'm going to show you guys how to do this on TI-84, and I'm going to show you again how to do this on a Desmos. The difference between life and death is often just minutes when it comes to stopping bleeding. 2 emergency procedures are being compared for their speed in stopping bleeding at the scene of accidents. The time from when 911 is called to the time that paramedics reported the bleeding stopped is recorded for each procedure. So again, good times with CPM, right? Hey, you want to talk about people bleeding out in a math problem? Let's go ahead and do it. So procedure C has all this data. Procedure I'm sorry, C2 has all this data, C7 has all this data. That 2 is procedure C2, that 7 is procedure C7. So your teacher will show you how to make a combination histogram and modified box plot on your graphing calculator. So what I did was I downloaded a TI-84 simulator. You might have access to this. I use a weird operating system called Ubuntu. I think it's available probably for Microsoft and Apple maybe as well. I don't know. But it works just like a regular calculator that you might see. Again, a lot of you guys on apps, I know you've already downloaded apps. Again, I think it's free on the Android, and I think it's like $5 on an Apple if you want to download the TI-84 app. I don't think it's a bad idea. I think it's actually a way better idea maybe than actually buying a TI-84 because they're so expensive and they work the same. Although you can use it on the SAT and that kind of a thing. So I've already pre-slugged some of this data in. If you'll remember, you go turn it on, you go stat 1, and I've already input the data for C and L1. I'm sorry, C2 and L1 and C7 and L2. So if you'll recall, what I want to do is I want to check my data now and make sure I didn't screw this up. So I'm going to go to variable stats and watch what happens when I do. I'm going to say L1 and L2 and I'm going to calculate because essentially I want to do my checksums. And it says that I have a problem. And the problem is that C2 is a longer list of numbers than C7 is. So what that really means is that if I want to check my data, which I do to make sure I have my checksum, I actually need to do one variable stats. Two variable stats is when you have equal column length, but if you don't have equal column length, you have to do them one at a time. So I'll go here, I will calculate, I have a checksum of 182, so I feel good about that. I will go here, place in a little bit right here. So I'm gonna talk for another minute or two, then it's gonna go back to the original video. After I did 10.1.4, it occurred to me, now would have been a good time to have also explained some of these other numbers. When we go through, I think this is the mean, this is a summation, this is if you squared the values. These two we'll talk about more later. N of 20 just means that there's 20 pieces of information in that column. But these are the ones I wanted to show. We're about to make a box and whisker plot, and this is the data. So this would be the smallest number in the data. This would be quartile 1. This would be the median. This would be quartile 3, and this will be the maximum. So again, you could get your range by subtracting the minimum for the maximum, getting a range of 26, and you can get your interquartile range by subtracting 4.5 from 10. You'll see that I keep going through and making the box and whisker plots, and it shows the minimum, quartile 1, median, quartile 3, and maximum. But again, I want you to see that this actually comes up when you run the one variable stats as well. All right, now back to the normal video. And I will change this to L2 now. And I will go calculate, and you can see that I have a checksum of 153, so I feel pretty good about that. And now what I need to do is I need to make a modified box plot where the outliers are shown separately. We'll kind of talk about all this as we go. We need to choose our bin width and all that good stuff. So long story short, I'm going to go up into my plots, and I'm going to do two plots. So I'm going to turn on the first plot. And the first thing I'm going to do is I can choose different kinds of plots. So I can choose a histogram. And that is one of the plots that I want, is a histogram. I'm going to hit enter, and it says L1. That's great. So I'm going to have one plot that's a histogram. And then I'm going to make the other plot. Again, I need to turn this on. But on this one, I don't want any of these. I want one of these two. These are both box and whisker plots. But you'll notice this box and whisker plot has outliers, which they told us to use that one. This one doesn't. So in theory, either one of them would work, but this one is going to show outliers. So I'm going to hit enter, and again, you'll notice that they're both for L1, which is really important. You want to make sure you don't have like L1 data for the box and whisker plot and then L2 data for the histogram. So I'm going to go to the graph, and you're going to see I have some sort of issues here. I'll go zoom 9 like we always try first, and that's looking a little bit better, but you can see that there's some kind of interesting things going on here because the calculator has chosen this data for us. So what I can do is I can go to the window and I can change some of this stuff. Now, I know that I have like 20 pieces of data. So the square root of 20 is 4 point something, so like 5. And I also know I want about 5 bins. And I also know that the smallest number is like 2 or 3, and the biggest number is like 29. So think about it. I want my smallest bin to be, and I guess I'll go back over here. I want my smallest bin to be 0, and I want my biggest bin to be 30. And I'm gonna have about 5 or 6 bins, so I could go by 6s, which would be, I think, a little bit weird, but I could do that, right? I get 1, 2, 3, 4, 5 bins. And this is a lot of what this chapter is about, is you guys, and this is one of the reasons I really like this chapter, is you guys making your own decision, right? It's easy for me to tell you, oh, you should do this, but I want you to think for yourself what makes sense, because you can have more than one right answer. So 1, 2, 3, 4, 5, 6. So I can have 6 bins instead of 4.5 bins, which it's fine, that's close. Plus, my bins will go by 5, which I think makes more sense. So I think that's what I'm going to shoot for. I am going to make my smallest x value 0. I'm going to make my biggest x value 30, right? Because 29 is the biggest one. I'm going to make my scale go by 5s, like we talked about. My y value, really, I can have it go to 0. I'm not going to have any negative values. And what's the most amount of things am I really going to have in each bin, right? I might have 3 or 4 or 5 in each one. So I'll make my y scale go to like 10, although I doubt I'm really going to need it. And I just want to see what that looks like. See if that looks good or not. So yeah, I mean, you can see we're getting closer to where we want to be. But it looks like my window, it only goes to 10. What if I push the window up? If I push the window up, to my y scale up to like 20, say, that would make this one go down. So I'll show you what I mean. If I make my y scale go to 20 instead of 10, now when I look at this, my bins are way smaller. So you can see that just by making the y scale go up to 20, it pushed all this data down. So if I had like 10 numbers and it went to 10, then it showed the whole column. But now if there's 20, it only goes halfway and it shows this data. You can see I have some outliers here. What I would do at this point is I would like literally handwrite. I would go over here and I would be like, all right, here's what my scale looks like. I have my scale from 0 to 5 to 10 to 15, and I would have my box and whisker plot, and it would look however it was going to look, and my histogram and my box and whisker plot, and it would look however it was going to look. And then I would do the same thing, and I would know that this was C2, right? And then I would do the same thing for C7. And I would have the scales right on top of each other. And I'm not sure if you're really following what I'm saying right now, but I'm going to do this in Desmos, and I'll show you exactly then. But then we can make straight comparisons, right? Because they would be literally right on top of each other. So I would hand draw again. I would take this and I would hand draw this on a scale. Then I would compare it to, all right, well, what happens when I change this to L2 data? So now I'm going to go with my second data instead of my first data. So now this will be the C7. So I'm going to go up here. I will change this to L2 as well. I'll look at my graph, and you'll notice my scale is exactly the same. Like, I've already changed this window from 0 to 30 by 5s, from 0 to 20. So now I'm looking at exactly apples to apples when I compare them on top of each other, and my comparisons make sense. Now what I wanted to do was take you over to Desmos and show you how to do the same thing in Desmos. So you'll notice what I did this is the C2 data. I actually just wrote L equals, I put a bar, and then I just typed all this data in. Okay, this is all those 20 pieces of data. Then I did the same for M. And I typed M equals, I put this bar, and I put all this data in. Essentially what I've done is I made two lists, one named L and one named N. Now, and this is how easy Desmos is, I say, hey, I want to make a box plot of the data that's in L. And so I think it looks something like this originally. It made the data of L. And then I said, all right, cool. Well, I want to make, and again, I think it looked like this originally. I've already played with this a little bit. I said, I want to make a histogram of the data in L. And it went like that. And it was done by ones. Well, again, you'll see the data set is L. The bin width is 1. I want to change that to 5. So now that's kind of what we were looking at. Oh, by the way, I think it was also centered around the number here. You can see that's like in the middle. I changed it to left so it would look like the calculator. But the problem I have is that that box plot is right in the middle of my data. So I can do this offset and I can sort of move this up. I think I actually chose 15 for later. So you have this box and whistle plot. One limitation that I have noticed in Desmos, and I don't know if this is something that's changed, but I haven't figured out how to do it. And when I Googled it, what I found was that you can't do outliers. The outliers won't show up like it did in the other one. But that's not the world's biggest deal. So I have this data here. Now I can do the same thing for M. I can go M, and you'll notice I changed that to 15. You'll notice it's like right on top of the other one. And then the histogram for M, I changed the bandwidth to 5. Well, it's kind of in the way, so what I can do is get rid of these two. And then what I did was I did a screen capture of both of them, and I put them next to each other and just sort of copy and pasted. So we can sort of compare this data to each other. Again, we would have done the exact same thing with the calculator that we had here. We would have done the same thing. We would have just handwritten a little scale, use the exact same scale, and it would have looked the same, except for the TI-84 would have had a couple of outliers on this side. And again, we can't do that in Desmos, at least that I'm aware of. Not yet anyway. They'll probably add functionality. I think they always add functionality, so they're always trying to make it better. But anyway, so let's analyze this data. Which one would you rather call? Well, it's an interesting question. Remember, you're bleeding, and the longer you bleed, the worse it could potentially be. So if we look at C2, look how much better the median is on C2, right? That's a direct comparison. You'll notice my scale goes by 5s to 30, and this goes by 15. So like this is a direct scale. Half the calls are already done in C2, and we barely got started, right? They've already stopped half the people from bleeding, and on C7, they've got like the shortest one they've done at that point. So if you want it done quickly, it looks like C2 is the way to go. However, you'll notice C7 is super consistent, right? You're pretty much going to bleed for between 5 and 15 minutes, and that's it. Well, in C2, you might bleed for like 2 minutes, or you might bleed for like 30 minutes. And depending on how much you're bleeding, we could run into some real problems over on this end of the table, right? So beauty's in the eye of the beholder here. Which one would you choose? Well, it would depend on a lot of factors. And again, this is kind of how I want you guys thinking about this. If I was bleeding profusely, and I was going to die if I bled for like 5 minutes, I guess I'd take my chances over here, because they're not getting anything done that quickly, right? So I'd be like, hey, look, they might get here in 30 minutes, or it might take 30 minutes, or whatever the procedure is, but at least on this one, I have an outside chance and the bleeding stops super quickly. If it's like moderate bleeding, but enough that I'll die if it goes too long, like what if they say, hey, look, if you bleed more than 15 minutes, you're toast. Well, I sure as heck don't want C2. C7 will, it's going to take care of me fine. So again, it's one of those things. If you think about it like sports, let's say you have a guy that hits a lot of home runs, but he strikes out a lot in baseball. Well, depends on the situation. If you got two guys on and there's 2 outs in the 9th inning, yeah, if you get a 3-run homer, that'd be great. But if you're in the middle of a rally, you probably don't want that guy to come up and strike out. You might just take a single hitter instead that has a higher average. So again, everything is situational, and there's more to this than just meets the eye straight by looking at it. And that's something I want you guys to consider as we do these chapters. All right, so that I think answers 1043. I know there's a lot to it. Please watch the videos or watch other people's tutorials on how to use TI-84 and Desmos. If I left you confused, I apologize. So 1044, center shape, spread, and outliers. When you describe the relationship between two variables on the scatter plot in chapter 4, it took several statistics to get a meaningful description of the data: form, direction, strength, and outliers. Again, if I say my fence weighs 900 pounds, that doesn't give me nearly as much of a description as if I tell you how long it is, what it's made of, how tall it is, right? You need all that information, not just one piece. So when we describe data, we want to use a bunch of different things. So similarly, it takes several statistics to get a meaningful description of single variable data, like the sales prices of houses in Fancyville and Smallville. Comparing the medians alone didn't tell us a useful story. Again, comparing the means alone didn't tell us a useful story, but when we combined the two, we started to get a better picture. So statisticians like to report center, either median or mean. And again, I want to be very clear on this. Median's always okay to use. Mean, you should only use in a normally distributed bit of data if it's normally distributed. If you have a tail or if you have outliers, you don't want to use mean because those outliers or that tail can screw it up. But if it's normally distributed, mean's okay. That's the center. When we talk about shape, actually I'm going to save shape for last because I want you guys to see in a little bit the math notes. When we talk about spread, we're talking about the interquartile range and the range, right? How big is the interquartile range? How big is the middle 50th percentile? Or how big is the total range? What's the difference between the poorest person and the richest person? Is there a big range or is there a small range? So spread is talking about range, and then outliers, like we said. We're not going to have like a textbook definition of outliers in this class. There's more than one way to calculate an outlier, by the way, which I think is interesting. The math hasn't pinned that down to just one way to do it. So there's a couple different ways that you can define an outlier that I'm not going to get into in this video because it'll take a while. But like I said, the last thing I wanted to talk about was the center. I'm sorry, the shape. So if you go to the math notes in 10.1.3, we get to the shape. And really all we're going to be looking for in this class is it symmetric, right? Is it sort of uniformed? Even if it's, we'll be doing a lot with single peak symmetric. That's the bell-shaped curve, the standard bell-shaped curve. So symmetric is really what we're looking at, or it's going to be skewed. That's not a very good tail. And a skew just means that it either has a tail on one side or a tail on the other side. So this is skewed left, this is skewed right, or it's got that long tail on either the left or the right. Again, if it's sort of uniform, where you sort of have just distribution where you have just as many smalls as bigs, then it's known as symmetric. Hope that makes sense. Again, outliers are calculated several different ways, and we don't do much with them in this class. You'll do more in stats if you ever take it. You don't do a lot with outliers in integrated 2 either, which is surprising. Whatever, this is probably a long video. I apologize for how long this went, but it was a big section. There's a lot in it. And again, I hope that you're following along with those notes and sort of filling some of this stuff in, and just know that you're responsible for all this stuff, so make sure you're learning it. Best wishes. Have a great day.